Here is the cross-section and the schematic diagram of a stainless steel golf club head. As you can see from the diagram, the stainless steel golf club head is hollow. This allows the golfer to swing the golf club easier. For the description of the material, this material is also known as A2 stainless steel. This material contains a high percentage of iron with chromium up to 18% and nickel up to 8% and small amounts of carbon. This material is also considered to be an austenitic stainless steel, which will be explained later. A specialty of this material is that it has a higher corrosion resistance than regular steel and can withstand corrosion from more oxidizing acids. However, this material is susceptible to corrosion from chloride solutions or saline environments such as the coast, because chloride ions create pitting, where the ions corrode a concentrated area.
To understand the microstructure of 304 stainless steel, we need to know the properties of the 304 stainless steel. This steel has a crystalline structure. Its grain size can vary from fine grain to coarse grain according to the treatment given. On the left side, we can see that the stainless steel is annealed at 780 degrees Celsius for 5 minutes and it produces a fine grain 304 stainless steel. On the right side, the 304 stainless steel samples are annealed at 1100 degrees Celsius for 15 minutes and this produces a coarse grain 304 stainless steel. 304 stainless steel that is used in this case, which is golf club, is the 304 stainless steel of smaller grain size so that the product is a stiffer product. And the 304 stainless steel contains approximately 18% chromium and 8% nickel.
The austenitic phase is unstable and gets transformed into martensite during forming. This is due to strain rate, and temperature. Even though martensite enhances strain hardening, which causes the delay of necking, the martensitic phase raises forming load, reduce formability, and decrease corrosive resistance. For further deformation, annealing is required. However, this will cause production to slow down and cost to increase. To overcome this problem, researcher has explored warm forming of stainless steel.
A study was carried indicated that warm forming of stainless sheet reduces martensite formation when forming at elevated temperatures. This research performed drawing tests of cylindrical cups made of types 304 and 316 stainless steel. Next, tests were carried out at room temperature of 90, 120, and 150 degrees Celsius. It is observed that the limiting draw ratio, LDR, becomes remarkably higher in warm deep drawing compared with drawing at room temperature. From the graph shown, it can be seen that LDRs obtained at different temperatures from experiments and simulation for type 304 stainless steel displayed good correlation. From the two figures below, we can see the relationship between the temperature and the limiting draw ratio, LDR. From the left figure, warm forming at room temperature causes the cup to fracture at an LDR of 2.2. As for the right picture, warm forming at 120 degrees Celsius allows the cup to be drawn much deeper at an LDR of 2.7. Next, we proceed with the relation of microstructure and properties of 304 stainless steel. The effect of cold rolling reduction on the viscous hardness is shown in figure 5. The hardness values were found to increase with cold rolling. The cause of this change in hardness with cold rolling reduction may be attributed to the effect of the increased dislocation density and the formation of strain-induced martensite introduced by cold deformation. The viscous hardness increased from 200 to 600 due to the applied cold rolling.
The engineering stress strain curve of the 90% cold rolled specimens is shown together with that of the primary sample in figure 6. It can be seen that the primary sample shows low yield strength of approximately 300 MPa, the ultimate tensile strength of approximately 600 MPa, and a large fracture strain of approximately 50%. After the 90% cold rolling, the strength is greatly increased to approximately 1825 MPa, which is nearly 6 times higher than that of the primary one, with a great loss of the fracture strain, which is 7%. They found that the ratio of the average tensile strength in MPa to the average viscous hardness in different percentages of cold rolling was constant and equal to 3. However, the ratio of the average yield strength to the average tensile strength with increasing percentage, which is up to 50% of cold rolling, tends towards one value. In the present work for 304 stainless steel, the ratio of the average tensile strength to the average viscous hardness for as received and 90% cold rolled specimens were also constant and equal to 3.